Hello and welcome to this video. In this video we're going to be looking at Newton's law of gravitation. So this is the first equation that pops up on your formula sheet for the gravitational field section, and this is because it's the basis of the rest of gravitational fields. The first thing we have to look at is how the forces behave in this field. As soon as we can get a grasp of how the force between two objects behaves, then we can understand much more about it. Since we know that all of the motion that we've done in AS mechanics has always been caused by some sort of force acting on something. So orbitals or orbits or orbital motion or I don't know, satellite motion or something like this, these have to be explained by the forces of gravity that are acting on things. So what we're going to say is Newton's law of gravitation is that F, the force, is equal to G, which is called Newton's gravitational constant, times big M, small m over r squared. Now this is the law. Now I'm just going to specify this is still a vector. Okay, force is still a vector, always will be. This G here is the gravitational constant, which is 6.67 times 10 to the minus 11, and its units are Newton meters squared per kilogram squared. Okay, this you don't have to memorize, obviously. It's in your formula sheet. It's on the first page, but it's a constant. Okay, this is always going to be the same. Now, as a side note to this, just something a little bit interesting, this is actually the worst measured constant, some would argue, in all of physics, because we've already said gravity is a very, very weak force in terms of looking at all of the forces. We have to go to scales of planets and stars to actually be able to observe the effects of gravity. And so we're not actually entirely certain of how accurate this value is. It's pretty accurate. It's accurate enough to apply to calculations, and the calculations are correct with it. When I say accurate enough, I mean that in order to be an accepted value, this thing has to be measured to be like 99.9999% accurate by teams of scientists. So maybe that will inspire some of you to devote your life to just researching what this value is, see if you can get a better result than 6.67 times 10 to the minus 11. But now, Newton's law of gravitation is described by this equation. You'll notice I've got two m's, and that's because I just have two different masses. If I have a gravitational force, it has to be between two different masses. So sometimes you'll see this written as m1 and m2. It means exactly the same thing. It's not possible to have a gravitational force just between one thing, because what's it being attracted to, right? We know gravity is an attractive force, it has to be attracted between two things. Sometimes in a question they will ask you to state what is meant by Newton's law of gravitation, or define Newton's law of gravitation, or things like this. So we need to also be able to explain this in terms of words. Now when we write this out as sort of like a sentence or a paragraph, whenever we convert equations into words, we always just want to talk about the proportionalities in that equation. In this equation, it shows us, since G is a constant, that the force is proportional, or let's be more specific, is directly proportional. Directly proportional to the product of two masses. Okay, so the product of the two masses is m1 times m2, and is inversely proportional to the square distance between them. Okay, where r is the distance between these two bodies. Okay, so this is how you would get your marks if the question were to ask you to explain Newton's law of gravitation or state Newton's law of gravitation. Okay, now The key thing with this is it follows a few ideas, or from this simple equation we can grasp a few things about the force of gravity and how it behaves. The first and probably most important thing is that this force is a vector, okay? But forces have to act on something. And in this equation, we're not specifying which force or which body or which two of these masses is the force actually affecting. Is it pulling mass m1 to m2? Is it pulling mass m2 to m1? And you might expect that to be like, okay, we know the bigger mass is going to pull the smaller mass towards it. That would just be logical, right? But actually what we find is when we do this calculation, if we were to say the force acting on m1 and then we use this equation, it would be the same as if we just switched the place of m1 and m2. This means that if I have the Earth here, so let me draw it as a point mass for now, this is the Earth, and then I have the Moon over here. Just as the Earth pulls the Moon towards it, the Moon also pulls the Earth towards it. And actually what we find is these two forces have the same magnitude. Okay, so these two forces, so the Earth pulls the Moon, by the same amount of force as the Moon pulls the Earth. Okay, so actually quite an interesting result really, because it means that we're not actually being orbited by the Moon. The Moon doesn't go around us. We are just seeing that because we're standing on Earth. We say that we're stationary, and then from our perspective it looks like the Moon's going around us. But if we were to then all transport over to the Moon and then stand on the Moon, it would look like the Earth is going around us. So actually these two things from an outsider's perspective seem to co-orbit each other, okay, because the force between them is the same. The centripetal force that's keeping the Moon traveling around the Earth in a circle is the same force that's keeping the Earth traveling around the Moon in a circle, which also we can apply to the Sun around and the planets around the Sun. It's still a two-way system. They're both co-orbiting each other. Now, from here, we then want to investigate how does the force then change as we move away from the surface. So as we increase the distance between these two things, how does that force actually vary? So what I'm going to say is I'm going to scroll down here and I'm going to rewrite Newton's law of gravitation. So this is gm over r squared. And I'm going to take an example of the Earth here. And let's say I have a test mass here. Okay, so this is just some mass m. It's not the Moon. So this is just a mass which I've labeled m. Okay. Now the distance between it is going to be called r. Now for the moment I'm treating this as a point mass. Okay, because I can just say this distance r is big enough that it doesn't actually the radius of the Earth doesn't contribute towards the distance away. Okay, we'd say that this must be at least 2 orders of magnitude bigger than the radius of the Earth. So the way the force would look at this point is we know that as the equation says that F is inversely proportional to 1 over r squared, or inversely proportional to r squared. Now the masses of these two things were going to stay constant. Just because we're moving something doesn't mean that its mass necessarily has to change. It is possible for its mass to change, for example a rocket, but in this case it's just a block of metal that we're just going to launch into outer space. And what we can say from this is that as r increases, F must decrease. Okay, so for very large values of r, we're going to get a very small force. Okay, so we could put this point here. Then we could say if we did the opposite and we decreased r, so we got as close to this as possible, F is then going to increase, and we're going to end up with a relatively small r is going to go up to this. Now If you wanted to be more spot on with this, we could test the limits. So usually in physics, when we test limits, we say, what happens if this thing goes to 0, and what happens if this thing goes to infinity? And actually, if r tends to infinity, that means that r squared tends to infinity, okay? If not, well, definitely even faster than r will tend to infinity. And actually that means if r tends to infinity, what happens to the force? Well, gmm is constant, so that's not going to change if the distance changes. But if we then divide by infinity, the force then becomes 0, okay? Technically, if you wanted to be very mathematical about it, this would be called undefined, since we don't actually know what dividing by infinity is. But we're going to say, for logical purposes, in this scenario, it makes sense to say 0. What this means, though, is that we have to travel an infinite distance away to feel no force, okay? To make it absolutely 0, we have to go to infinite distances away. And this is why the range of gravity is infinite, because you actually have to travel an infinite distance away to escape that field, okay? Which means it doesn't matter where you are in the universe. If you're standing somewhere, you have gravitational attraction to every other massful object in the universe, okay? Which is a pretty profound way of thinking about life. But then we need to test the other limit. So what happens if r goes to 0? And if r goes to 0, then f tends to infinity. But physics dictates that if we have an infinite force, that requires infinite energy, because we have to keep accelerating this thing, and it's going to keep getting faster and faster and faster. It's going to have infinite kinetic energy. That's not possible, okay? So this limit here can't be correct, okay? Physics doesn't allow this to be possible. So that's when we're saying, if we're zooming in and we're getting closer so that this distance between the point mass and the small mass decreases, that's when we have to come out of the point mass approximation. We have to actually treat the Earth as a sphere. Okay, so now I'm going to change this, and just to fill this in, this is going to be an r squared curve, so that it looks like a reciprocal curve like this, and I've done it only up to where r is the radius of Earth. Okay, now if we wanted to go to the spherical Earth, let's say we get so close so that this distance r here is no longer big enough to neglect the radius of the Earth. So the radius of the Earth is RE, and RE is given in your formula sheet, and it's given in your formula sheet as 6.37 times 10 to the 6 meters. This is the average radius of the Earth. Obviously the Earth isn't a perfect sphere, but we're approximating here, okay? That actually means that the total distance from the center of this field, which is the center of mass of Earth, if we're considering this a perfect sphere, the center of mass of a perfect sphere is dead in the center of this. The distance between them, so the center of mass, so the center of this field, and the actual mass that's in the field, is the sum of RE, so the radius of Earth, plus whatever distance it is away from the surface of the Earth, which I'm actually going to redefine as h. So this is the height above Earth, and that means this is now going to be a distance from the center, okay? Now the interesting thing that we can say now is what happens when we get to, if we can go to r equals 0, okay? What happens when we start going inside the Earth? How does that change? Okay, because if we're then under the Earth, by the equation of Newton's law of gravitation, surely when we're decreasing r to 0, we should feel infinite force dead at the center. But if you were to be pulled into a position and you stay at that position, you will feel no force. Okay, imagine being on a bungee cord, for example, and you get pulled, or a horizontal bungee cord. So let me draw this out. Some of you might have seen, you can have this kind of bouncy castle thing where you have a bungee cord attached to you here and you try and run as far as you can. The force currently acting on you is pushing you back this way. If you were to just stand here in the position that you're being pulled to, you don't feel any force from that bungee cord. Okay, if you go to the origin of that cord, you will then feel no force based on that. If I go to the center of Earth, I will feel no gravitational force. So what I can actually say from here is, if I decrease this gravitational field such that R goes to 0, if that means I'm at the center and I know at the center I have 0 force, then surely I should go through the origin of this graph. I should have a force of 0 when the radius is 0. And this is true. This is what happens. But how does that then affect what happens between the distance of r equals 0 and the radius of the Earth? What happens when the point mass m is here? What kind of force does it feel then? Does this change exponentially? Does this change quadratically? Is it linear? These are the kind of questions we have to ask. Now, we don't have the mathematical tools so far in our studies to actually be able to prove that this is the case. But any of you who want to go to university to study physics, you will prove this many times over for both this and electric fields and all the rest of it. If you go inside the mass of the Earth, the way I'm going to explain it now is, if you're inside the mass of the Earth, this outer shell worth of mass is no longer contributing to your pull inwards. So it's no longer contributing to your gravitational force. Now, some of you watching this video will say, but this is still a mass. Surely this mass should pull it this way, and then this mass should pull it this way, and you'd be right. And what happens is, when we calculate that, we find that there's actually no residual effect of the mass pulling it out. It's a negligible effect in general. But as it starts to do this, you're slowly decreasing m, and you're decreasing m as r increases or decreases. And if m, the mass of big M here, is directly proportional to f, as f, or as we should go with, as r decreases, f is also going to decrease, which means f must be directly proportional to r. And this is true. Now, this isn't a proof, okay? You can't use this as a proof of this being true. You need way more maths to actually prove that this is true. But this shows a linear relationship. It means that as I now enter the Earth, the force will fall like this, and it will eventually be 0 only when I'm at the center of the field. If I go infinite distance away, it doesn't matter how far I go, I will never reach 0 unless I'm at infinity or I'm at 0. Those are the two cases. So the things that you want to take from this video are this Newton's law of gravitation, the fact that this force is equal when it's felt by the two bodies or the two masses, this idea of an inverse square where I have this curvature, so I can go to infinite distances and only then will I get 0 newtons. So the range of gravity is infinite. And then this idea that as soon as I now go back down into the surface of the Earth, so I get close enough to the Earth that I can no longer approximate it to be a point mass, I then have to change the way that Newton's law of gravitation looks. So it will no longer have this expression. So this only holds when outside the Earth, or let me just say outside the mass. Okay, because it doesn't always have to be the Earth, but it only holds true when you're outside, because only in this region here is f proportional to 1 over r squared. As we just said, in this region, f is proportional to r. Okay, thank you for watching.